Today we are going through short answers exercises. Question 34. Why is the ultraviolet portion of the electromagnetic spectrum not the microwave or infrared red portion used to sterilize medical instruments? The ultraviolet portion of the electromagnetic spectrum is made of sufficiently high frequency, which means high energy electromagnetic radiation that can destroy bacteria or other pathogens. Question 35. The electromagnetic spectrum is continuous and there is no sharp division between one kind of wave and the next. Assuming that the preceding statement is true, how do physicists distinguish one type of electromagnetic wave from another? Electromagnetic waves are distinguished by their different frequencies and wavelengths. Exercise 36. Why did early experimental attempts to measure the speed of light fail? The speed of light is so great that it could not be measured given the limitations of early measuring instruments. How are the terms luminous flux and illuminance related to each other? Luminous flux is a measure of the amount of light emitted from a light source. It is measured in lumens. Illuminance is a derived unit that indicates the relationship between luminous flux and the distance from the light source squared. Illuminance is the ratio of lumens per square meter. How is the brightness of a light source affected by distance? Question 38. Brightness decreases by the square of the distance from the source. Question 39. What type of reflection is illustrated in the figure shown above? To understand what type of reflection, we need to see the direction of reflected light rays. The direction of the reflected light rays in this case are not parallel. Because they are not parallel, we are going to have diffuse reflection. Question 39. What type of reflection is illustrated in the figure shown above? Again, as we said in the question 39, we are going to see the direction of reflected light rays. In this case, the direction of reflected light rays are parallel to each other. Because the reflected light rays are parallel to each other, the kind of reflection is specular. Question 41. If a light ray strikes a flat mirror with an angle of incidence equal to 52 degrees, what is the angle of reflection? Explain. The angle of reflection is going to be 52 degrees. This is according to the first law of reflection, which says that the angle of incidence is equal to the angle of reflection. If a light ray strikes a flat mirror at an angle of 61 degrees, so there is an angle between the flat mirror and the incident light ray which is 61 degrees. What is the angle of reflection in relation to the normal? Again, it is given the angle between incident light ray and the mirror which is equal to 61 degrees, and we need to find the angle of reflection as it's shown here in the figure with question mark. The angle between incident light ray and the mirror is equal 90 degrees minus theta, the angle of incidence. We are going to rearrange this equation and to solve it for theta. After we are going to substitute the values, we'll find out that theta is equal 90 degrees minus 61 degrees is equal 29 degrees. So the angle of incidence is 29 degrees. But we know, according to the law of reflection, the angle of incidence theta is equal to the angle of reflection. Therefore, the angle of reflection is 29 degrees from the normal. The answer is 29 degrees from the normal. Question 43. Translate into words the following mathematical relationships that are observed with flat mirror reflection. We have P equal H and H equal H prime. What does this mean? This means that the object is distance P is equal to image distance Q, and object height H is equal to image height. Describe the reflected image of a flat mirror in terms of distance height, real or virtual, and reversed or not. The reflected image of a flat mirror is virtual, appears to originate from a distance behind the mirror that is equal to the object's distance in front of the mirror, has the same height as the object, and is reversed. The focal point and center of curvature of a spherical mirror all lie along the principal axis. Question 46. What is the sign for object and image distances that are measured on the front side of a mirror? Positive. If an object or image height is negative, where is the object or image located in relationship to the principal axis? Below the principal axis. The height of an object is 4 cm. Its image height is 12 cm. What is the magnification? Is the image upright or inverted? Is the image real or virtual? In this case, what is given is the height of the object, which is 4 cm, and the height of the image, which is 12 cm. We are going to substitute these values into the equation for magnification. The equation for magnification is equal the height of the image over the height of the object. We are going to solve it, and then the result is 3. So, the magnification is 3, and since magnification is positive, the image is upright and virtual. An object's distance P is 20 cm, and its image distance Q is 10 cm. What is the magnification of the image? Is the image upright or inverted? Is the image real or virtual? Let's see. In this case is given the distance of the object from the mirror, which is 20 cm, and the distance of the image from the mirror, which is 10 cm. We are going to use the equation for magnification. The equation for magnification in this case is m equal minus q over p. To find the magnification, we are going to substitute the values which we have for q and p, and the magnification is going to be minus 0.5. Since the magnification is negative, the image is inverted and real. A line parallel to the principal axis is drawn from the object to a spherical mirror. How should the reflected ray be drawn? Through the focal point F. A line is drawn from the object to a spherical mirror and passes through the center of curvature C. How should the reflected ray be drawn? Back along itself through C, through center. A line is drawn from an object to a spherical mirror and passes through the focal point F. How should the reflected ray be drawn? Parallel to the principal axis. What type of image do flat mirrors always form? The flat mirrors always form virtual image. What is the chief difference between real and virtual images? The chief difference, the main difference between them? Real images can be displaced on a surface, virtual ones cannot. Spherical aberration may be avoided by employing a space mirror or by making sure that the diameter of a spherical mirror is sufficiently. So what kind of mirror we have to employ to avoid spherical aberration? Parabolic mirror. And then the diameter of a spherical mirror is sufficiently small. Let's carry on with the problems. The frequency of a gamma ray is 6.54 times 10 power 18 Hz. What is the gamma ray's wavelength? What is given is the frequency and the speed of light. To find the gamma ray's wavelength, we are going to rearrange the wave speed equation. The wave speed equation is c equal frequency times wavelength. We are going to isolate the wavelength and calculate it. So the wavelength is equal c over f. After substituting the values of the speed of light and the frequency, the wavelength lambda is going to be 4.59 times 10 power minus 11 meter. A portion of infrared light in the electromagnetic spectrum has a wavelength of 727 nanometers. What is the frequency of this portion of infrared light? Given is the frequency and the speed of light. Again, one more time, we are going to rearrange the wave speed equation. C equal frequency times wavelength. We are going to isolate the frequency from this wave speed equation and we'll calculate it. The frequency is equal speed of light over wavelength. After substituting the values, we are going to find that the frequency is equal 4.13 times 10 power 11 Hertz. A concave mirror forms a real image at 17.9 cm from the mirror surface along the principal axis. If the corresponding object is at a distance of 35.3 cm, what is the mirror's focal length? What is given is the distance of the object from the mirror, P, which is equal 35.3 cm, and the distance of the image from the mirror, Q, which is equal 17.9 cm. To find out what is the mirror's focal length, we are going to use the mirror equation 1 over P plus 1 over Q equal 1 over F and solve it for F, for the frequency. So 1 over frequency is equal 1 over distance of the object from the mirror plus 1 over the distance of the image from the mirror. After substituting the values, we are going to find that the focal length is 11.9 cm. Problem 59. A concave mirror with a focal length of 19.9 cm forms a real image at 29.5 cm from the mirror surface along the principal axis. How far is the corresponding object located from the mirror surface? What is given is the focal length, which is equal 19.9 cm, and Q, which is the distance of the image from the mirror, and equal 29.5 cm. To find the distance of the object from the mirror, we are going to rearrange the mirror equation. 1 over P plus 1 over Q is equal 1 over frequency, and we'll solve it for P. So 1 over P is equal 1 over F minus 1 over Q. P is equal 61.0 cm. So the distance of the object from the mirror is equal 61 cm. A candle 15 cm high is placed in front of a concave mirror at the focal point. The radius of curvature is 60 cm. Draw a ray diagram to determine the position and magnification of the image. To draw a ray diagram, we have to draw 3 incident light rays from the object to the mirror, one parallel to the principal axis, the second one passing through the center, and the third one passing from the focus. After we draw these three incident light rays, we are going to find that when the candle is at the focal point, the image is infinitely far to the left and therefore is not seen, as shown in the answer diagram. So, as you see here in the diagram, we are not going to see the image because the image is infinitely too far to the left. 61. An object is 15 cm from the surface of a spherical glass tree ornament that is 5 cm in diameter. Find the magnification and location of the corresponding image in relation to the mirror surface. Draw a ray diagram to confirm the position and magnification of the image. What is given is the diameter, which is equal 5 cm, and P, the distance of the object from the mirror, which is equal 15 cm. To draw a ray diagram, first we have to draw 3 incident light rays from the object to the mirror. One parallel to the principal axis, the second one which is passing through the center, and the third one which is passing through the focus. After drawing these incident light rays, where they intersect with each other, we are going to find the image. Now, to find the magnification and location, we are going to do as follows. Since the diameter is equal 5 cm, the radius is going to be 2.5 cm. And since the ornament acts like a convex mirror, the focal length is equal minus 1.25 cm. Let's rearrange the mirror equation, which is 1 over p plus 1 over q equal 1 over f, and solve for q. 1 over q is equal 1 over f minus 1 over p. After substituting the values, we are going to find that the distance of the image from the mirror is equal minus 1.15 centimeter. Since q, the distance of the image from the mirror, is negative, the image is located 1.15 centimeter behind the mirror, or inside the ornament. To find the magnification, we are going to do as follows. Magnification is equal the ratio of minus q over p, and the magnification is equal 7.69 times 10 power minus 2. And now we are going to the last problem and the last exercise for this revision. A 1.5 centimeter high image of a candle is formed by a convex mirror. The virtual image is 3 centimeters from the mirror surface. The image's magnification is 0.25 positive. Draw a ray diagram to determine the position and height of the corresponding object. Use the equation for magnification to confirm the results of your diagram. So what is given is the height of the image, the magnification, and the distance of the image from the mirror. It's negative, so it means that it's behind the mirror. So, in this exercise, the image is given behind the mirror. Here is the mirror, and at a distance 3 from this mirror, we are going to draw the image. The image is high 1.5 centimeters, so at a distance 3 centimeters, at a height 1.5 centimeters, we are going to draw the image. At the top of this image, we are going to draw 3 light rays. One which is going through the focus, one which is going through the focus, the other one which is going through the center, and the other one which is parallel to the principal axis. After we draw these 3 light rays, where they intersect, we are going to find the object. Now, we are going to use the equation for magnification to confirm our results. To confirm our results, we are going to use the equation for magnification. The equation for magnification is equal the height of the image over height of the object. We have the magnification, which is 0.25. We have the height of the image, which is 1.5 centimeter, and from this relation we are going to find the h is equal 6.0 centimeter, means that the object's height is 6. Since h is positive, so since the height of the object is positive, means that the object is located above the principal axis, Use the equation for magnification again. We are going to use this equation minus q over p and solve it for p. Once we solve it for p, we have q and we have the magnification. We are going to find that p is 12 centimeter. So we have an object which is at a distance 12 centimeter from the mirror, and height is equal 6 centimeter. Since q, the distance of the object, since p, the distance of the object from the mirror, is positive, means that the object is located in front of the mirror 12 centimeter. And this was all for this revision. Thank you for watching.